This recording is basically to talk about a 4x1 multiplexer and a 2x4 decoder design. So without wasting my time, this is the 4x1 multiplexer. Don't mind how I saved it. The 4x1 multiplexer. So with 4x1 multiplexers, you need some series of 2x1 multiplexers in order for it to be able to work. And basically, this is a 2x1 multiplexer. Maybe you might know something called the max tree. Yeah, it's a series of multiplexers which has been compiled to form integrated and complex maxes. But that's multiplexers. That's the shortcut for multiplexers, the max. So here I have a simple 2x1 multiplexer, and I can integrate this and make it an advanced multiplexer by doing so. So let me wipe up the top here of the top here. You see, with this, now initially it was having one, two inputs. That was what made it a 2x1 multiplexer. But since I integrated another 2x1 multiplexer on it, it currently has one, two, three, four. That's four multiplexer. That's a 4x1 multiplexer. So right now we have two, three 2x1 multiplexers, which actually gave us a 4x1 multiplexer. Get it? And this can also be found with this formula. Let me wipe the place and write it. When you have let's say eight, sorry, when you have an 8x1 max and you are asked to find the number of the number of 2x1 multiplexer used in forming this 2x1 max. Asked to find the number of 2x1 max, 2x1 multiplexers used in forming the 8x1 multiplexer. You just have to use this step. You have 8 as the higher order number and 2 as the lower order number. So basically divide the 8 by 2 and we get 4 for it. Then divide this 4 again by 2. This 2. When you divide, we get 2. Again, you divide again by 2. Here we get 1. There is one rule. You divide the higher order number by the lower order number until the the final number you get is 1. It's 1. Let's say if here was supposed to be 3, let's say, sorry, 3, and I divided. Sorry for the inconvenience. As I was saying, if here was to be 3, and I was supposed to find the number of 2 by 1 multiplexers in it, that will be 3 divided by 2, which will give me 1.5. And it's not possible because you can't have a 3 by 1 multiplexer, because a multiplexer accepts dual, a 2 by 1 multiplexer accepts dual inputs, just like we saw it. So you will find the number of 2 by 1 mux in it, not the number of 3 by 1 mux. You get me? So let me take a different example with this. I'll be using a 64 by 1 box, and you are supposed to find the number of 2 by 1 box. Sorry for the writing, I'm using mouse, so it will be a little bit unseeable. So with this, I'll divide 64 by 2, which will give me 32. And now, I once again divide the 32, bring it here, 32 by 2, and I get 16. If I divide again, 16 divided by 2, I'm getting 8 for it. Let's bring the 8 here. So 8 divided by 2 again, I'm getting 4. And this 4 divided by 2, I'm getting 2. Now 2 divided by 2 is equal to 1. Again, now I've ended at 1, so there's no way I'm supposed to divide this again since I've ended here. So now I want to find the number of 2 by 1 mux in it. Right now I'll add the solutions I got from dividing the 32 mux by the 2 by 1 mux, the 64 mux by the 2 by 1. I'll add all the solutions I got throughout my division process, which will be 32 plus 16 plus 8 here. Where's the eraser? Plus 8 plus 4 plus 2 and plus 1, and that will give me 63. So basically I used 63. Sorry, there's one problem here. This 32 is included, so when you are adding, make sure you include it. That's how you get a 63. If you exclude it because you think it's too big, you might get in trouble. So the addition of the outcomes was 63. So basically you use 63 2 by 1 mux in order to form this 64 by 1 mux. You get me? So now with this concept, let's go get down to the main task. That's this. We are supposed to build this. This has already been built. I'll just explain it more. And if possible, I might start afresh for you guys to be able to get it. Yeah. So I've trying to make some notes down. That's what I'm using to do the explanation. Because with this, you are supposed to form this 4 by 1 multiplexer. And to form this 4 by 1 multiplexer, you need to know the number of inputs you are going to receive. And with this, the number of inputs is going to be 4 because it's a 4 by 1 multiplexer. There is one formula for the 4 by 1 multiplexer. We have a formula to determine the type of multiplexer. That is the 2 exponent n times 1. Basically, this is the formula for finding the type of multiplexer when you are given the inputs, where n is equal to right, where n is equal to the where n where n is equal to the number of selection lines. The number of selection lines. And to find the number of input, the number of input is 2 exponent the n. This is equal to the number of input to be received. And as we all know, with a multiplexer it only has one output. So when the conditions are true to it, then it outputed. With this here, there is we have a box form of indicating illustrating a multiplexer. That is for 2 by 1. If this, let's take it as if this is my multiplexer. This here is my multiplexer, and it's a 2 by 1 mux. It's a 2 by 1 mux. So I would have sorry, I would have this input here. That is my I naught and my I1 and my selection panel, which is S. Since with a 2 by 1 mux it will only be a 1, as the formula said, as we said with the formula, the number of inputs to be received is n times n exponent 2. That's 2 times, if it's 1, 2 times 2, if it's 2, 2 times 2 times 2. Again, if it's 1, then it's the same. That's 2 exponent 1. 1, 2, sorry, 2 exponent 2, 4, exponent 3, 8. Yeah, that's simple. So when this increase, the number of inputs also increases. When the number of selection lines is increased, the number of input to be received is also increased. We here, since it's a 2 by 1, it's a 2 by 1 mux, we have 2 exponent n, where n is equal to number of selection 1, because we are saying it's a 2 by 1 mux. So 1, then 2 exponent 1 will give me 2. That's why we have 2 inputs here. So with this, its output, it's only it has only one output. There's only one output, which is y. And with y will not work or give you any value when you enable when you've not enabled your mux to work. If you haven't enabled your mux, there is no way to work. So with diagram form, it's very important to include this right here. Very important to bring this right here when they are asked to draw a diagram representing a 2 by 1 matrix. Well, so as I said, let me clean this and let's talk about a 4 by 1 max. So with a 4 by 1 max, the box diagram for a 4 by 1 max is as follows. As we said, 4 by 1. So if it's 4, that means it's 2 exponent 2, and n is equal to 2. N is equal to 2, where n is equal to selection line. So here currently now I have 1, 1, 2 selection lines. With this, that means I am also clear that I have 1, 2, 3, 4, and this here are my inputs. I can have this here, I naught, I naught, I1, I2, and I3. And this here will be S0, S0, and S1, S0, sorry, and S1. So my output, as we already know, it's only one way. My output is only one way. And with my enable function, my multiplexer will work. So this is my 4 by 1 max. This is my 4 by 1 max. And there is we have a boolean table for it. Let's go back to work. Let's go back to work. Let me insert my tables. Let's say I need 1, Currently, we are working on a 4 by 1 month. Uh, as I was saying, with my word, I'll have here as I'll have here to be my control E. So here would be my enable caps lock 20. Here would be my enable. Here would be my S not. S not. Here would be my S1, and here will be my Y. As you can see, this wouldn't be enough, so let me go to layout, set now, set. So if the enable function, that's my enable indicator, if it's not on, if I have not enabled it, here not being enabled is 0, then all inputted values for any input option, that's either I1, I not, I1, I subscript 1, I2, I3, I, whatever you input, when enabled hasn't, when your mux hasn't been enabled, it wouldn't work. So with here, all values wouldn't be able to be read in the selected selection lines, that's the S0 and S1. So it will automatically give you an output of them. But when it has been enabled, then you would have four different types of inputs for it, which would be 0, 0, which would actually give us for I1 and not. Then 0, 1, which would be I1, then 1, 0, which will give me I2, and 1, 1, which will give me I3. Sorry, which will give me I3. So with this boolean table, I can actually deduce uh, an equation for it, where I would have y to be equal to, which is my enable. Since my enable is running through all, let me bring that one out to multiply all of the function. Now my enable, and so with the table, since my enabling is going to be throughout the process, I'll comment that one. I'll bring that one out to multiply the whole uh, equation. Then I'll move to this with I1. With I1, that's what I'm saying. With the with the equation for y, since they are never be going throughout, I'll bring that one out to multiply it. Then we take this for I naught. When you see with I naught, we are having zeros for both the select line one and select line one and select line naught. Yeah. So that means it will be actually be denoted by the S bar, the S naught bar, and the S1 bar. The bar shows the negative form of the one, which is the zero. Bar is used to indicate zero. So you have for I naught, S naught bar, S1 bar plus I1, S naught bar, S1 plus I2, S1, S naught, sorry, I2, S naught, and S1 bar. Is here. Then for I3, we have S naught, which is here, and S1. Since none of them is zero, we wouldn't have to include the bar on top. So this equation would actually be used to draw or design the 4 by 1 multiplexer. So with this, I can say, let me copy this here. This is my equation. I've placed my equation on top of my pen so that I'll be able to see it clearly. So with here, so I know what is there. Since pen doesn't accept the equation symbols, that's why it's giving me a question mark. So yeah, I know what is there. So now let me a problem. As I said, there we have AND gate and OR gate. This is an AND gate. This is an AND gate. This is an OR gate. This is a NOT gate. And this is what is used to negate any value into a zero. This is what is used to in the diagram or in a circuit to indicate the value entered is a zero, or it converts one to zero, a zeros to one. So if you want to convert a one input to a zero, use this, or a zero input to a one, you make a pass through this, it will be automatically converted into one or zero of your preference. So I'll then just waste time here. As I was saying, with the how the with this here, and bring it down here. Okay, up here, yeah. So with this here, I'll be building a simple circuit from it. So using this to, let's say I'm building this specific input, then I'll have my AND gate. I'll have my AND gate open, which is I have my AND gate situated at where I want it, and I'm receiving values. So let me reduce my values to what I want as before. So basically, I want just an input for this one. 3. Since 1, 2, 3. If I'm receiving an input for this, it's, let's say this goes to my S1, this goes to my S2, and this is for my input. That's where my user input is value. So I'll be using this to form this. But before that, I'll clear this. I'll clear these so that you'll rebuild it and see how to build it on your own and how it should be able to function when you build it. This table would be of help to the rest. So let me see. Okay. So I'll need one, two, three, four inputs. Four inputs. So one, two, and bring here. Three, four. So now I have my AND gate. One, two, three situated. This will be for my inputs. This will be used to receive my inputs. This one is not for input, but it's used to receive my inputs and add them together to process the function before it brings out the output. And I have a negative, that's a 0 in it, so I'll have to introduce my NOT gate. Let me place my NOT gate somewhere here. I need two NOT gates, so here, and this is my OR gate. This will be used to link all the inputs which will pass through the AND gate, and it will be receiving 1, 2, 3, 4. So I change it here. The number of inputs it should collect 4. It reduces. Then I connect this to this, then this to this, then here to here, and finally here to here. So with this in place, my my AND gate has been linked to my OR gate, but we need an output. This, let's put our output here. Let's put our output here and link our OR gates also to our output. It has been linked. Fine. Let's move on. We also need places to input our values so that it will pass through the gate. Let's put our input tab, our input location here. One, another input location. Let me use this line. Two. I can copy, paste. Another one, 3. And another one, 2 here, 4. So now I have to link at least one tab, one port to my input location. And this is not supposed to have 5 inputs. We are actually working with 3 inputs, which is the input and the select line. So I'll reduce the port size to 3. I'll reduce this 2 to 3, this 2 to 3, this here to, I'll reduce it to 3. Let me reduce it to 3 then to solve that problem. So reduce it to 3. This won't be important. Now let's link one port to our tap. Let's bring it here. First one has been linked. Second one has been linked. Third has been linked. Fourth has been linked. So now we are done with linking it. Now we are coming to focus on how to use the the equation here to continue with our diagram. Before that, we also have bring input for our OR gate. Yeah, we link the first one here. Then another input for our OR gate again. Yeah, let's bring it further apart more. Link that one to here. Bring this one to here. So now all the linkages have been done. Now, when you come to a word here, you can see the equation here. The first equation is y not with, and you are supposed to map it with s naught bar and s1 bar. So let's indicate it here. I not, in order for us not to get confused when working, I1, I2, I3, and this will be my select not and select one. Okay. So now with all things done, I'll come back to it. As I said, I not maps with S not bar and S1 bar. So if it maps with S not and S1 bar, then let's drag or let's link them all to our NOT gate. Let's link them to our NOT gate. Let's link them to our NOT gate. Now it has been linked to our NOT gate. After linking to our NOT gate, you can choose to test it out, because it says when S1 is 0 and S2 is 0, I1 should work. When you check it, it's exactly the same. You see, the output has been lit up, meaning that I1 is working. Let me change it. You see, it will cut. It wouldn't work. If I turn it back to 0, it will work. So I put it off. Then we go back to continuing building it up. Now I'm done with I1. Then let me focus on I2. I'm done with I0. Let me focus on I1 next. With I1, I'm supposed to map it with S naught bar and S1. But how would I map it to S naught bar when I've already mapped S1 bar to I1 bar to S1 and S naught bar already? So the advisable thing is you tap into the part of the S1 and the S there's already the S naught bar and the S1 naught part. So I link this to this. After that is done, now with the S1, how am I going to get to S1 here? S1 is here. So like I'm confused. You shouldn't get confused with it. This is the only simple way to do it. You link it down into the part of the S1 before you link it to the NOT gate, so that whenever the you start this operation, you turn this input side on, and it will be able to pull out some of the current and use it for its operation. Now, with that said, let's try that one out and see. With S1, it says I S naught should be 0 and S1 should be 1. As we already saw it. When it was 0, S1 was working, S naught I naught was working. Let me turn on I1. You see, currently I1 is not working. This is the path to the end gate, the OR gate to the output. And since I1 is not working, let's see the criteria for I1 to work. It's actually for S0 to be off and S1 to be on, which is S0 to be 0 and S1 to be on 1. So if I turn this one to 1, you see the path has automatically changed from the S1 not trajectory to the S I1, sorry, the I1 not trajectory to the I1 I1 trajectory. So that's how the thing is. Let me put it off, or I can actually keep each and every one on for you to see. You see, currently we haven't finished working on this. So you see, immediately I enabled the input. It just went through because the criteria hasn't been set for it. So it just accepted any rubbish it received, you see, and gave us some unneeded output. But let's continue with it and you find out what is actually interesting about this. So back to working and completing the circuit. Our third one to look about is the to look on is the I2 and the I3. So let's take the I2. With the I2, we are supposed to have S0 and S1 bar. See, just like I said, S0 and S1 bar. So with my S0, I come down, come down here, then I leave it there. Then with my S1 bar, since I've already connected S1 bar to this, I'll just tap into its part. Let's go ahead and complete the last one before we test it out. With the I3, I would have to have S1 and S0 all positive number. So with that, S1, this is S1, S0, this is S1. This code will actually work perfect. You can also choose to tap in here. You try that one out. So let me minimize it. So with this, now let's test it out and see. When I put when it's on 0 0 and I put 1, I not on, I not gives me an output. If I change it to 0 1, you see with 0 1, when I turn on I1, I1 gives me an output. I1 gives me an output. Currently, see, after completing, when I turn on all the input sides, I haven't been having any multiple outputs there. So with the selecting lines to be 0 and 1, where I S0 is 0 and S1 is 1, we have I1, and for I2 to work, we are supposed to have I0 S0, sorry, S0 to be 1 and S1 to be 0. So immediately I change it, the path has lit up, meaning that this is working perfectly. And for the last one, as we said, we are supposed to have S0 to be 1 and S1 to be 1. When this is turned to on to 1, the path has automatically been lit up. So this is it for the 4x1 multiplexer. We'll be moving on to the 2 by 4 decoder, where, as I said, decoders it accepts multiple inputs and also gives out output. It has multiple output path, but one is active at a time. And in case where you are active, there's how to fix it. But now we didn't be going there yet. So, with the multiplexer, it has been done already. Now we are going to work on this, which is the decoder. This is a decoder I've already worked on. You see, when we have input for decoder 00, output 1 has been taken. If you have decoder 01, output 2 is being taken. If it's 10, output 3 is being selected. And if it's 11, output 4 is selected. So now let me input this. Let me input this in. This why not? This y1, y1, y2, and y3. Then we have here to be I1, I1, you decided to like what? And I2. So now this is our I1. This is our I2. Our I1 is here. Our I2 is here. We have our Y not. Sorry. I not. Sorry. I not and I1. So let's talk more about it before we get down to building the code. With the decoder, we're working on the 2 by 4 decoder, and it normally goes with which also has a formula to be 2 times. Sorry, the formula actually is n times 2 exponent n, where n, as you already know, the number. We are all in that. We are paying attention. As you know, n is the number of inputs. Sorry, n is the number of inputs, and 2n is equal to the number of outputs. So with this, let's use this formula to test out some examples and see if it actually works. So we have a n. We have n, or let's say a 3 by 8 decoder. How are we going to test? You see, right here we have 3, and this one can be broken down to the original form to be 2 exponent 3. And actually, we are able to see that here 3 and 3, which is the n, is equal to each other, or they are the same. Basically, meaning that the formula n times 2n has been satisfied and is correct. When we take a 4 by 16, a 4 by 16 decoder, we would have it to be 4 times 2 exponent 4. 2 exponent 4. And 2 exponent 4, it's 16. You get it? 2 exponent 4. And so 2 by 4 is 16. You have 2 times 2 times 2 times 2. This will give us 4, 8, and 16, which also satisfies the rule n times 2 exponent n for the formula for finding the number of decoders, the input and the output a decoder will have. So without much ado, let's move straight. We'll be working on a 2 by 4 decoder. So me having my 2 by 4 decoder, I'll be using a box diagram to explain it. I have my 2 by 4 decoder, a 2 by 4 decoder, and I have here to be my input 1, here to be my input 2, since it will be accepting to input, and I would have my output here, which is 1, 2, 3, 4. That's 4 output for it. Here will be I naught, and here I1. Here I'll have here to be Y naught, Y1, Y2, and Y3. So if I have my input here to be 0 and here to be 0, Y not to be selected? Same again, if I have my input here to be 0 and here to be 1, I1 will be selected. Again, if I have here to be 1 and here to be 0, I2 will be selected. And if I have both input sides to be 1, 1, then I3 will be selected. I'll be using a Boolean table to help us understand it more. So, and moreover, our enable is supposed to be on for that. If the enable is off, you're actually going to have problems. So let's jump to the red document. In here, you see we have a table of values and letters and figures or something or whatever I see here is whatever I see there. So as for me, the here is for the enable. This is for the input 1. Alright, that's supposed to be I naught. I naught, and here the I1. So as we said, when enable is off, both values wouldn't be recognized. Therefore, all 4 outputs will be given as a 0 output. If enabled is on, we'll be having 4 different possible inputs. That possible input which is 0, 0, which will give us 0, 0, 0, 0. As well, why not to be selected? And 0, 1, then gives us 0 on Y3, 0 on Y2, 1 on Y1, and 0 on Y0. For Y1, for I naught to be 1 and I1 to be 0. Y is equal to 0. Y is Y naught 0, Y1, Y naught 0, Y1 0, Y2 1, and Y3 will also be 0. For the last one, the last input parameter, if both are 1, then we have Y3 to be 1 and Y2 to Y0 will be 0. This is a sample decoder I just drafted. As you can see, if I1, I0 is 0 and I1 is 0, I have here Y0 to be on. If I have 0 and 1, I have Y1 to be on. If I have 1 and 0, I have 1 2. If I have 1 1, I have Y3 to be on. So these are my output and this is my input. So we'll be going to drop this from the whole video. So to do a decoder design, you have to input your decoder, and that will be found at the plexus. Go to the plexus, you locate decoder, place it, then you change the number of bits to 2 in order for you to be able to accept more values. With the number of bits as 2, you'll be able to accept 4 values. That means, as we said, with 2, you'll be able to accept 4. With 4, you'll be accepting 16. With 3, you'll be accepting 8. So we are building a 2 by 4 decoder. That means we have our bits to be 2. And we shouldn't be including enable here, because we will be enabling the decoder with the commands we have. So put enable to 0. No. Then this is your output pin. So you select your output pin, then you copy and paste. You are supposed to have 4 outputs. 4 outputs. 4 outputs. We have my 4 outputs in there. Now let's link the output to the decoder. Have our first output linked to the decoder. Our second output so linked to the decoder. Third output linked to the decoder. And the last one also linked to the decoder. You see, after there are no other ports. When I put it here, I'm not able to locate the port like this one. Again, that means I'm supposed to know it's only up to 4 outputs it can produce. Then we insert our input value, our input pin. Let's place our input pin here. Then map it to the decoder. With this map, we are supposed to change this number of data bits. We are supposed to accept two data bits. The data bit is supposed to be 2, so we change it from 1 to 2. And when we change it to 2, the decoder has started working perfectly. We are ready to change it to 2. Now we have it there. Let's indicate our 13. I have Y1, Y0, Y1, Y2, Y3. You have here to be I1, I0, sorry, and I1. And this, let's reposition them in order to be able to see them clearly. Now that the decoder has been built, it's now time for you to test it and find out if it works actually like the way you expected it to. So when we come here, we have our first input to be zero and second to be zero. And with that, we are supposed to see why not is supposed to be active. So here we have why I not to be zero and I want to be zero. Why not has been selected. Now let's change this. We have I not to be zero and I want to be one. And when I one is one, I two, I one, Y one sorry, Y one is selected and Y one is active. And we go again. We are supposed to have I want I not to be one and I want to be zero. When I one is equal to zero and I not is equal to one, we have Y2 to be selected, which has been indicated in the table. And lastly, if both inputs are 1, we have Y3 to be selected as the input, which is currently here. So, actually, this brings us to the end of the presentation on how to go a 4 by 1 multiplexer and a 2 by 4 decoder. Thank you.